Hi, everyone. This is Yuxuan. I just finished out my second year at the University of Michigan. And today, I'm excited to present our work, Training with Confidence, Catching Silent Deep Learning Training Errors with Automated Proactive Checks. This is joint work with Ziming Zhou, Boyu Xu, Beijie Liu, Runhui Xu, and my advisor, Professor Huang. In this talk, I'll introduce the TRAINCHECK system and how it detects silent training errors before they wreck your training jobs. Let me begin with a real story to show you the kind of problem that we're dealing with here. Hugging Face trained a large language model called Bloom in 2022. It had 176 billion parameters. The compute resource was very expensive, and the engineers were working hard to make sure the training process is correct. The loss curve looked very smooth. Perplexity was improving. Everything pointed to a healthy training job. However, something had actually gone quietly wrong at the very beginning of training. A bug in this speeds optimizer caused model weights to desynchronize across GPUs. There was no crash, no error message appeared, but under the hood, the checkpoints produced during training will be invalid, and the entire 3.5 months of training could have been wasted. This is a classic example of what we call a silent training error, where training seems to be fine, but under the hood, something subtle is broken, and by the time it is caught, it might be too late. And Bloom is far from a corner case. PyTorch's GitHub repository has a dedicated label for silent errors, and other large-scale projects like Meta's OBT175B encounter 17 mysterious loss explosions. Bloomberg GPT had a bug in their BERT implementation that caused weight decay to be silently applied to all parameters. At the Shanghai AI Lab, over 60% of their GPU time was spent on canceled jobs instead of completed or crashed ones, indicating prevalence of silent errors. So silent errors are prevalent, hard to catch, and extremely costly. What can we do to detect these silent training errors early on? Our contributions are twofold. First, we conduct an empirical study of 88 real-world silent training errors drawn from GitHub issues, Stack Overflow posts, and industry incident reports. We learn common patterns and root causes of silent errors. And based on the insights, we developed TRAINCHECK, which is an automated system designed to identify silent training errors early on. Let's start with the empirical study. So first, we found out that silent errors, they have very diverse root causes, originating from all possible layers of the DL stack, from hardware, compilers, to user code and frameworks. No layer is safe. This means that single component testing solutions might not be enough to protect the actual training process. Even if your own code is bug-free, you could still hit issues from a bad GPU or a subtle framework change. What we need is end-to-end runtime validation in order to catch these errors as they happen. Additionally, silent errors are challenging to detect, and the delays in detection can have severe consequences. The evaluation metrics that people mainly rely on to measure training correctness can appear non-deterministic. For example, the Bloom divergence error never manifests in these metrics at all. Additionally, these metrics can be too noisy to determine whether an issue truly exists. This suggests that an early detection method should go beyond evaluation metrics. Finally, many silent errors, despite their high-level non-deterministic appearance, they do stem from precise and actionable root causes, like API misuse, kernel faults, or network glitches. These components have well-defined specs, so their behavior should be more predictable. This implies that non-determinism is only an artifact of checking at the too high level, and it can disappear when viewed at the right level of abstraction. That brings us to our core idea, training invariants, which are low-level properties that should always hold during training. By checking for violations, we can catch silent training errors early on. To make this more concrete, let's revisit the Bloom divergence error. So the reason behind the divergence was that gradient clipping was only applied to the first worker within each tensor parallel group. The root cause is shown in this API called getGradForNorm, shown here. It serves two purposes and uses a flag called forClipping to determine which one. When forClipping is set to false, this API collects the gradients to compute the total gradient norm. At this point, you want to deduplicate parameters that are shared across workers so that each logical parameter is only counted once. But when forClipping is true, it collects the gradients that will actually be clipped. And here, no deduplication should happen. Every worker needs to apply clipping to its full set of gradients. However, in this buggy version, the deduplication logic was mistakenly used for both cases, so only the first worker ended up applying clipping, while the others skipped it. This caused model weights to silently diverge. Now, what kind of invariants could have caused this? One example is an API contract invariant on that API called getGradForNorm, ensuring that when forClipping is true, the function returns all gradients without deduplication. Another is a parameter consistency invariant, checking that certain parameters, like layer norm weights, remain consistent across all workers in a parallel group. If these invariants had been monitored during training, the issue would have been detected as early as the third iteration, when gradient clipping is first applied. With such early detection, developers could have paused the ROM and fixed the issue before it silently degraded the entire training. We designed TRAINCHECK to automatically infer these training invariants and continuously validate a target training ROM. TRAINCHECK systematically covers a wide range of silent errors and can be seamlessly integrated into existing workflows. On a high level, TRAINCHECK combines the offline automated inference stage with an online proactive validation stage. So in the offline stage, the instrumenter instruments correct pipelines and produces execution traces. These traces are fed into the inference engine, which extracts invariants. And in the runtime stage below, the verifier checks a target training pipeline against the inferred invariants. If violations are found, it raises alerts. In the rest of this talk, we will focus on the invariant inference engine and briefly touch on the instrumenter. Here are the key challenges our inference engine must tackle. First, the invariants that we infer needs to be semantically meaningful, not just any low-level patterns, but checks that reflect DL-specific logic. Secondly, DL training pipelines often have very limited, DL training behavior often depends on subtle runtime context. A critical semantic might not be statistically prevalent. And third, DL training pipelines often have very limited development history. That means the invariants that we infer should be transferable across runs, setups, or even different code structures. Finally, the search space is massive. A single iteration of GPT-2 pre-training can log 50 megabytes of trace data, so efficiency is essential. To address these challenges, first, TRAINCHECK represents invariants in a flexible yet precise way. Each invariant has three parts. First, a relation, like consistent, that defines the rule to be enforced. And secondly, a set of descriptors that abstracts over concrete API or variable instances observed in a trace. This allows invariants to generalize across different runs without being tied to exact names in your code. Third, a precondition which describes when the invariant should apply. For example, this one only applies to layer norm weights, which accounts for less than 1% of all parameters in transformer architectures. This structured form lets us express complex behaviors clearly and reason about when they are valid. TRAINCHECK automatically infers invariants in three main steps. First, we scan the reference traces for potential patterns. Each time we detect a match, we form a hypothesis about what might be an invariant. And second, we validate each hypothesis by checking it against all reference traces, collecting both passing and failing examples. And third, for hypotheses that don't always hold, we identify their preconditions, which encode the context under which they are valid. To instantiate invariants, TRAINCHECK uses a set of domain-specific relations that reflect common DL semantics as extracted from our empirical study. For example, consistent checks if two variables stays in sync. Event contain ensures one event happens within the duration of another. We scan training traces to instantiate these templates into concrete hypotheses. This target approach helps us narrow down the search space while ensuring that the inference stays relevant to DL-specific behaviors. After generating and validating all the hypotheses, we try to infer a precondition for it. So for each hypothesis, we compare the examples where the invariance holds to those where it fails and looks for a precondition that explains the difference. If we find such a precondition, we keep the invariant along with each precondition, and if not, we'll discard it. Preconditions are just conjunctions of simple rules about variables' attributes, API arguments, context managers that are currently active, or some meta variables, like a field always having the same value, or being different, or even just existing. Unlike prior tools, TRAINCHECK treats precondition as a first-class citizen in invariant inference. This is key to make invariants both robust and transferable for DL systems. First, precondition define applicable context clearly, allowing transferability across different training setups. Second, many DL semantics are not statistically representative. Using precondition to determine invariant validity allows TRAINCHECK to preserve meaningful but context-sensitive invariants. It also prunes superficial correlations. For example, in the Bloom consistency invariant that we just talked about, it is pretty critical to training correctness, even though it only holds in 1 out of 39 cases. TRAINCHECK still accepts it as the precondition can be found. On the other hand, superficial invariants like a tensor's is CUDA and requires grad always have the same value. It holds 99% of the time, yet it's probably irrelevant to training correctness, and it will get rejected because TRAINCHECK cannot explain when this holds. To infer and check invariants, we also need visibility into how training behaves. And TRAINCHECK achieves this by dynamic instrumentation using monkey patching and proxies. No code changes are required from the user side. At the runtime, this instrumentation becomes selective to minimize overhead. So instead of recording everything, TRAINCHECK tailors what to observe based on the invariants that are to be checked. For example, to validate parameter consistency in Bloom, it only needs a single parameter dump per iteration, not every time it is changed. To evaluate TRAINCHECK, we collected and reproduced 20 real-world silent training errors. 6 were from our empirical study, and 14 were newly added. TRAINCHECK successfully detects 18 out of 20 real-world silent errors, and does so within just 1 iteration of training. It also helps with diagnosis. In 10 cases, it pinpoints the exact root cause, and in 8 more, it gets very close. In contrast, prior approaches like high-level metric monitoring detected only 3 out of 20 and pinpoint just 1 root cause. Along the way, TRAINCHECK also exposed 6 new bugs in deep speed and transformers. We also evaluate TRAINCHECK's false positive rate on 63 correct training pipelines, covering different frameworks, model types, and levels of complexity. Across the board, TRAINCHECK maintains a false positive rate below 2%, even with just 5 representative inputs. Another highlight is that TRAINCHECK doesn't need exhaustive input traces to be effective. In fact, we inferred all the invariants that's used to detect the 18 bugs with just a few example pipelines. For example, for silent errors related to PyTorch, even a single training script, GCN, would cover 77% of the errors, and just 3 simple inputs together covers all. Also, for the invariants that we inferred in the false positive evaluation, about 23% of them generalize across even different training tasks, and invariants with precondition do transfer than the unconditional ones. This suggests that invariants can be inferred once and reused across pipelines without retraining or reanalysis. We have a deeper analysis on this input detection trade-off in the paper. And finally, we measure the runtime overhead of TRAINCHECK by comparing the per iteration time before and after instrumentation. With selective instrumentation and 100 invariants deployed, the slowdown stays under 11% across all models. This makes TRAINCHECK practical to use even in large-scale training setups. To wrap up, silent training errors are prevalent, costly, and notoriously hard to detect. TRAINCHECK tackles this with a new approach, automated validation of training tasks using inferred invariants. By deducing when the invariants are expected to hold, we ensure precision and transferability across setups. TRAINCHECK is open source and actively maintained, and we would love for you to try it out. Now I'll take questions. Thanks.